Jain everyone. Myself Pooja Sharma. I am assistant professor in Computer Science and Engineering Department in Ajay Kumar Gar Engineering College. In today's lecture, we will discuss about the Apache Hadoop HDFS architecture. We know that HDFS is a distributed file system that is deployed on low-cost commodity hardware. So, these topics that will be covered in this lecture on Apache Hadoop HDFS architecture are as follows. First one is HDFS master slave topology. Second one is NameNode, DataNode, and secondary NameNode. Third topic will be what is block. Fourth one is replication management. Fifth one is rack awareness, and last one is HDFS read write operation. Okay, now HDFS architecture. Apache Hadoop HDFS is a block structure file system where each file is divided into blocks of predefined size. These blocks are stored across a cluster of one or more several machines. Apache Hadoop HDFS architecture follows a master-slave architecture where a cluster comprises of a single name node, that is master node, or all the other nodes are data node, that is slave nodes. HDFS can be deployed on broad spectrum of machine that supports Java. Okay, so this is the HDFS architecture. The master node store and manage the file system namespace, that is information about the blocks of files like locations, permissions and all. The slave node stores data block of files. The master node, that is name node, and data node are the slave nodes. So the HDFS architecture is built in such a way that the user data never reside in data nodes. Okay, now the HDFS name node. Name node is the master node in the Apache Hadoop HDFS architecture that maintains and manages the block present on data node, that is slave node. Name node is very highly available server that manages the file system namespace and control access to files by client. It records the metadata of all the files stored in the cluster. Suppose location of block is stored, the size of the file, permissions, hierarchy, etc. So, there are two files associated with the metadata. First one is FS image. FS image stands for file system image. It contains the complete namespace of the Hadoop file system since the name node creation. Second one is edit log. It contains all the recent change performed to the file system namespace to the most recent F changes. Okay, so now the functions of HDFS namespace. A name node, it execute the file system namespace operations like opening, renaming and closing file and directories. Name node manage and maintain the data nodes. It determines the mapping of blocks of a file to data node. It records each changes that takes place to the file system metadata. For example, if a file is deleted in HDFS, the name node will immediately record in the edit log. It regularly receives heartbeats and block report from all data nodes that ensure data nodes is alive. It keeps the location of each blocks of a file. The name node is also responsible to take care of the replication factor of all the blocks. Now, next one is HDFS data node. Data node are the slave node in HDFS. Unlike name node, data node is commodity hardware, that is a non-expensive system which is not of high quality or high availability. The data node is a block server that stores the data in the local files. So, functions of data node. DataNode is responsible for serving the client read and write request. The actual data is stored on DataNode. Based on the instructions from the NameNode, DataNode perform the block creation, replication and deletions. They send a heartbeat to DataNode periodically to report the overall health of HDFS. By default, this frequency is set to 3 seconds. Okay. Till now, we must have realized that the NameNode is pretty much important to us. If it is fail, we are doomed. But Hadoop solved this single point of failure problem by introducing secondary NameNode. So the secondary NameNode works concurrently with the primary NameNode as a helper daemon. So these are the functions of secondary NameNode. First one is the secondary NameNode is one which constantly read all the file systems and metadata for the RAM of the NameNode and write it into the hard disk or the file system. It is responsible for combining the edit logs with fimage from the NameNode. And it also download the edit logs from the NameNode at regular intervals and apply to FS image, and the new FS image is copied back to the NameNode, which is used when the NameNode is started to the start the next time. Now next is block in HDFS architecture. Now, as we know that the data in HDFS is scattered across the data node as blocks. Let's have a look at what is a block and how it is formed. Block are the nothing but the smallest continuous location on your hard drive where data is stored. The size of the block is 128 MB by default. We can configure the block size as per requirement by changing the dfs.block.size property in HDFS site XML. For example, if there is a file of size 612 MB, then how many blocks will be created? That is 5, right? The first 4 block of size 128 MB, you can see that 128 MB. There are 4 blocks and 1 block of size 100 MB. It means 128 into 4 plus 100 equals to 612. Okay, a file in HDFS are smaller than a single block does not occupy a full block size space of the underlying storage. Each file stored in HDFS does not need to be exact multiple of the configured file size. Okay. Now you must be thinking why we need to have such a huge block size, that is 128 MB. So the default size of HDFS data block is 120 MB. The reason for the large size of blocks are two reasons are. First one is to minimize the cost of seek. For the large size block, time taken to transfer the data from disks can be longer as compared to the time taken to start the block result. This result in the transfer of multiple blocks at the disk transfer rate. If blocks are small, there will be too many blocks in Hadoop HDFS and thus too much metadata to store. Managing such a huge number of blocks managing such a huge number of blocks and metadata will be create overhead and lead to traffic in a network. Now the how we find file size in Hadoop. Use the Hadoop fs-ls command to list file in the current directory as well as their details. So the output, the fifth column in the command output contain the file size in bytes. So this will be the output, and fifth column, it means this 45956 bytes is the size of the file. As we understood why a block is, let us understand how the replication of these blocks takes place. So next is replication management. HDFS provide a reliable way to store huge data in a distributed environment as data block. The blocks are also replicated to provide fault tolerance. The default replication factor is 3, which is again configure. The NameNode constantly tracks which block need to be replicated and initiate replication whenever necessary. Replication ensures the availability of the data. You can configure the replication factor in your HDFS site XML file. Property dfs.replications value is 1. It means replication, only one replication will be created. Okay, so this is the block replication architecture. Therefore, if you are storing a file of 128 MB in HDFS using the default configuration, you will end up occupying a space of 384 MB, that is 3 into 128 MB, as the block will be replicated 3 times and each replica will be reside on the different data nodes. The NameNode collects block report from the DataNode periodically to maintain the replication factor. Therefore, whenever block is over replicated or under replicated, the NameNode delete or add replica as per requirement. Okay, now let's discuss more about how HDFS plays replica and what is rack awareness. So, again the NameNode also ensure that all the replicas are not stored on the same rack or the single rack. It follows as inbuilt rack awareness algorithm to reduce latency as well as provide fault tolerance. So, the rack awareness algorithm says that the first replica of a block will be stored on the local rack and the next 2 replica will be stored on the different rack, that is remote location, but on the different data nodes within the remote rack. If we have more replicas, the rest of the replica will be placed on random data nodes, provided not more than more replica reside on the same rack if possible. Okay, next is advantages of rack awareness. First one is to improve the network performance. The communication between nodes residing on different racks is directed via switch. In general, you will find greater network bandwidth between machine in the same rack than the machine residing in different racks. So, the rack awareness help you to have reduced write traffic in between different racks, thus providing a better write performance. Also, you will be gaining increased read performance because you are using the bandwidth of multiple racks. To prevent loss of data, we don't have to worry about the data even if any entire rack fails because of the switch failure or power failure. Okay, now let's talk about how the data read and write operation are performed on HDFS. HDFS follows write once, read many philosophy. So, you can edit files already stored in HDFS, but you can append new data by reopening the file. Firstly, we discuss the HDFS write architecture. Suppose a situation where a HDFS client wants to write a file name called example.txt, that is of size 248 MB. Assume that the system block size is configured for 120 MB by default. So, the client will be divided the file example.txt into 2 blocks, one of 128 MB block A and other one of 120 MB block B. So the following protocol will be followed whenever the data is written into HDFS. First one is, at first the HDFS client will reach out to the name node for the write request against the two blocks, says block A and block B. And the name node will then grant the client the write permission and will provide the IP addresses of the data node where the file blocks will be copied eventually. The selection of IP address of data node is purely randomized based on availability, replication factors and rack awareness. Let's say the replication factor is set to default, that is 3. Therefore, for each block, the name node will provided the client list of 3 IP address of data nodes. The list will be unique for each block. Okay, suppose the name node provided following list of IP address to the client. For block A, list will be IP address of data node 1, second IP address of data node 4, IP address of data node 6. For block B, list will be IP address of data node 3, IP address of data node 7 and IP address of data node 9. Each block will be copied in different data nodes to maintain the replication factors consistent throughout the cluster. Now the whole data copy process will happen in 3 stages. First one is setup of pipeline, second one is data streaming and replication, third one is shutdown of pipeline, that is acknowledgement stage. Now first one is setup of pipeline. Before writing the blocks, the client confirms whether the data node present in each of the list of IP are ready to receive the data or not. In doing so, the client creates a pipeline for each of the block by connecting the individual data node in the respective list for that block. For block A, IP of address of data node 1, IP address of data node 4 and data node 6. Now, for block A, the client will be performing the following steps to create a pipeline. First, the client will choose the first data node, which is data node 1, and will establish our TCP IP connection. The client will inform data node 1 to be ready to receive the block. It will also provide the IP address of next 2 data node, that is 4 and 6, to the data node 1. Where the block is supposed to be replicated. Now, the data node 1 will connect to the data node 4. The data node 1 will inform data node 4 to be ready to receive the block and will give it the IP of data node 6. Then data node 4 will tell data node 6 to be ready for receiving the data. Next, the acknowledgement of readiness will follow the reverse sequence, that is from the data node 6 to 4 and then to 1. At last, the data node 1 will inform to the client that all the data nodes are ready and a pipeline will be formed between the client data node 1, 4 and 6. Now, the pipeline setup is complete and the client will finally begin the data copy or streaming process. Now, second is data streaming. As the pipeline has been created, the client will push the data into the pipeline. So, here block A will be stored to the 3 data node as assumed replication factor is 3. The client will copy the block A to data node 1 only. The replication is always done by data node sequentially. So, the following steps will be takes place during replication. First one is once the block has been returned to data node 1 by the client, data node 1 will connect to the data node 4. Then data node 1 will push the block in the pipeline and data will be copied to the data node 4. Again, data node 4 will connect to the data node 6 and will copy the last application of the block. Now, third step will be shutdown of pipeline or acknowledgement stage. Once the block has been copied into all the 3 data nodes, a series of acknowledgement will take place to ensure the client and name node that the data has been written successfully. Then the client will finally close the pipeline to end the TCP session. The acknowledgement happens in the reverse sequence, that is from data node 6 to 4 and then to 1. The data node 1 will push 3 acknowledgement including its own into the pipeline and send it to the client. The client will inform NameNode that the data has been written successfully. The NameNode will update its metadata and the client will shut down the pipeline. So, next will be the HDFS read architecture. This will be the HDFS read architecture. HDFS read architecture is comparatively easy to understand. Let us take the above example again, where the HDFS client wants to read the file, that is example.txt now. Now, following steps will be taking place while reading the file. First, the client will reach out to NameNode asking for the block metadata for the file example.txt. The NameNode will return the list of data nodes where each block, that is block A and B, are stored. After that, client will connect to the data node where the blocks are stored. The client start reading data parallel from the data node, block A from data node 1 and block B from data node 6. Once the client get all the required file blocks, it will combine these blocks to form a file. While serving read request of the client, HDFS select the replica which is closest to the client. This reduces the read latency and the bandwidth consumption. Therefore, the replica is selected which reside on the same rack as the reader node if possible. Now, next is what happens if data node fails while writing a file in the HDFS. While writing the data to the data node, if data node fails, then the following action takes place which is transparent to the client writing the data. The pipeline first one is the pipeline get closed. Packets in the acknowledgement queue are then added to the front of the data queue, making data node downstream from the fail node to not miss any packet. Then the current block on the alive data node get a new identity. This identity is then communicated to the name node, so that later on, if the failed data node recover, the partial block on the failed data node will be deleted. Third point will be the failed data node get removed from the pipeline and a new pipeline get constructed from the 2 alive data nodes. The remaining of blocks data is then returned to the alive data nodes added in the pipeline. The name node observe that the block is under replicated and is arranged for creating further copying or another data node, and other coming blocks are then treated as normal. So, this is all about the HDFS architecture. Thank you so much.